Hello, and thank you for attending this presentation for the International Conference on Advances in Construction Materials and Structures. My name is Alex Brand. I am an assistant professor in the Department of Civil and Environmental Engineering at the Virginia Polytechnic Institute and State University, otherwise known as Virginia Tech, in Blacksburg, Virginia, USA. Today, I'd like to give a presentation entitled Microstructure and Chemical Interactions in Concrete with Reclaimed Asphalt Pavement Aggregates. So before we begin, we should first define what is meant by reclaimed asphalt pavement. So this is the material that is produced from processing millings from asphalt pavements, such as during reconstruction, resurfacing, or rehabilitation. It should be noted that asphalt pavements, at least in the United States, are significantly more prevalent than rigid pavements or concrete pavements. Now, some of the latest data, at least in the US, is that there's currently around 110 million tons of stockpiled RAP. And that's as of 2018. Now, some of this recent data, again from 2018, it was reported that around 101 million tons of RAP were produced, while only 91 million tons were used, which essentially means that we're producing more RAP than is actually being used. And this number seems to be continuing to increase. So at least from 2017 to 2018, the amount of stockpiled material increased by 8% alone. So in other words, we do have a fairly large stockpile of this material. Now, of course, I'm giving this data for the United States, but if you look in the literature, it would appear that there are similar situations in other parts of the world. So there is also active research in India, in Brazil, France, and a number of other countries that have also been considering this issue of, if there's too much RAP, what else can be done with it? Okay. Now, one of the reasons why there is so much RAP, and particularly the coarse fraction, is that it's not feasible to recycle 100% of the aggregate in a new asphalt pavement or hot mix asphalt. It's not possible to, or it's not feasible, I should say, rather, to 100% replace all of the aggregate with RAP. The mixture properties just are not suitable for long-term performance. So the literature seems to suggest that only about 50% RAP is realistic. And at least the replacement amounts that are common seems to be only up to maybe 25%. So some agencies will perhaps increase that RAP content, particularly in lower layers, but at least for surface wearing courses, it would appear that the RAP content is limited to maybe 10 to 25% of the aggregate replacement. So again, this means that while asphalt pavements are significantly more prevalent, at least in the US, right, we're not producing so many pavements that we're able to utilize all of the actual RAP that is produced. In addition, and this may not be universal, but it certainly seems that some agencies are fractionating the RAP. We call that FARP, FRAP. So it's known as fractionated reclaimed asphalt pavement. And some agencies will fractionate it into coarse and fine fractions based on the number 4 sieve or 4.75 millimeters. Now, the fine fraction has a higher asphalt content, so that is much more commonly replaced into new asphalt pavements, particularly as a partial replacement of the asphalt binder. Again, because the fine fraction has a significantly higher asphalt content. So that means that the coarse FRAP, so the coarse fraction, so everything retained on the number 4 or 4.75 millimeter sieve, remains relatively unused. Now, again, that may not be universal, but it certainly seems some agencies have a significantly higher stockpile of the coarse material, right? at least for the research that I'll be presenting in this study, or I should say a few studies I'll be presenting on, we were mainly focused on this coarse fraction. So especially in densely populated areas, there's a significant issue with land use, right? So where is someone to store or stockpile this material, especially in densely populated areas, that there's just simply no land for it. So then there would be high disposable and hauling costs, right? So I should note that you know, stockpiling of this material is not universally an issue. So for example, in Blacksburg, Virginia, where my university is, it's a little bit more of a rural area. There's significantly more land available for stockpiling. But as you get closer to larger cities, particularly in my area, we're maybe about 4 hours away from Washington, D.C. So as you near that region, they have significant issues with stockpiling this material. There's simply not enough land, or it is too costly to stockpile it. So of course, there's the sustainability question of finding alternative uses for this material. Right. In addition, we can also consider, you know, options of partially replacing the virgin or natural aggregates in concretes as a sustainable option to, you know, use less natural resources. So instead of quarried material, for instance, and therefore that would be reducing our carbon footprint of the concrete per unit weight. Then of course there's a cost issue. Right, so it's possible that this RAP material is more cost effective than certain crushed aggregates. So anyways, there is interest in using this material, and if we look at a summary of the available studies. Now I should note that what I'm presenting here was a review article from 2016. You can see the citation there at the bottom. You know, so perhaps some of this information is a bit more outdated because there have been a significant number of studies in this area in the past few years. But regardless, I would expect a lot of these trends to similarly be found in some of these more recent studies. And what I would like to highlight is right here, right? And that is, at least for all of the studies that were surveyed for the review article at the bottom, basically all the studies unanimously agreed that as you increase the RAP content in concrete, you would decrease the strength properties and the modulus. And some of these other properties, you know, at least at the time, had perhaps not sufficient research available or data available to draw a conclusion. Again, a lot more of that may have been improved in the recent publications in the literature since 2016. Regardless, the focus of the remainder of this presentation is really the assessment of why is this happening, right? Because once we can establish why we see this reduction in strength and modulus, then we can perhaps start to assess what are some treatment or alternative designs to mitigate that, all right? And just to put some numbers here, so this is just from one study. You know, you'll see different numbers from other studies as well, depending on the mixed design and the properties of the RAP and so forth. But in general, at least from this study shown at the bottom that we published in 2015, we can see that replacing up to 50% of your coarse aggregates with RAP could potentially be reducing your tensile strength by 50%, could be reducing your compressive strength by maybe 40%, your elastic modulus by 30%, and your flexural strength by 20%. So fairly significant reductions, and that's only at a 50% replacement level. So if we were to you know, feasibly use greater proportions of this material as a replacement of our virgin aggregates, we would certainly have to find a methodology to mitigate the significant strength losses. Now, one of our early concepts, one of our early ideas was the simple thought that, well, asphalt has a lower modulus than the cement matrix or your aggregates. And while that is true, we found that that was not likely to be the dominant cause here. It may have an effect, but it's not the dominant cause. So what we're looking at here is, so first off, we do have the control mix here. So that this was with a dolomite, coarse aggregate, no RAP. And then we took our mixture that contained 50% coarse RAP, all right? And we tested the dynamic modulus of the concrete as a function of temperature, right? So as we go to lower temperatures, so as we get down to maybe around minus 20 degrees Celsius, the modulus of the asphalt will start to approach the modulus of the cement matrix. All right, and then similarly at higher temperatures, right, upwards of here we did up to 54 degrees Celsius. There, of course, the modulus of the asphalt is significantly lower. Right, but what we find is that the dynamic modulus does not appear to be dramatically affected by the temperature, right? And really, this is perhaps no surprise because once we go through the calculations, knowing how much asphalt was on the RAP, and in this case, it was, I believe, somewhere around 2.1%, right? Of the total volume of the concrete, the asphalt only accounts for less than 0.5%, right? So really, this led us to conclude that, more than likely the asphalt amount in the total concrete volume is really not sufficient to be the primary cause here, right? So this then led to the primary investigation that I'll be talking about here, and that is looking at the interfacial transition zone. All right, so in all concrete materials, the aggregates are surrounded by what's known as the ITZ, the interfacial transition zone, and it's essentially due to the wall effect. All right, so your cement particles have a finite gradation. Your cement particles, however, are much smaller than your coarse aggregates, for instance, right? So your mean cement particle size is somewhere around maybe 10 to 15 microns for a mean diameter, right? Your coarse aggregates now are of course on the order of millimeters, right? So significantly different sizes. So in essence, the cement grain sees the aggregate as essentially a wall, right? And so your grains cannot pack efficiently against that surface, right? Against that wall, if you think about it that way. So because of that, because the cement grains cannot pack as efficiently against the aggregate surface as it can in the bulk microstructure, all right, this forms the ITZ. Okay, and the ITZ can vary in thickness. It is going to depend on a number of parameters. For instance, simply just your water to cement ratio, right? Regardless, this ITZ is somewhere around tens of microns thick. It will tend to be more porous. It'll have a lower density as a result. There'll be less calcium silicate hydrate. There'll be less calcium hydroxide. There'll be less unhydrated cement. In addition, there will be more ettringite, right? Because the ettringite and the calcium hydroxide essentially have greater porosity to grow into. So you'll see large calcium hydroxide and more ettringite. So because of this, the ITZ is often regarded as the weak link of the concrete, right? This is the weakest part of the concrete. So your concrete's only as strong as your weakest component, right? So because this zone is more porous, has less CSH, it tends to be the lowest strength and has the lowest modulus of any part of your composite concrete. All right, so this is, at the very least, this is likely where cracks will propagate through, may also be where cracks will initiate, right? So that this would be the weakest point of your concrete. So The literature pretty much presents that there are three primary reasons why this is. So number one, the larger porosity in the ITZ, right? Already, so more pores, of course, already means that we'll have a lower modulus composite. It has been proposed that those large calcium hydroxide crystals that form allow for easier crack propagation. All right, so that can also be a problem. And then lastly is the actual interface between the aggregate and the ITZ. All right, so essentially that adhesion zone where the cement in the ITZ, right, so the CSH and things like that, actually adhere and bond to the aggregate. Okay, and so that interface now can have some type of mechanical bond that we can characterize, right? So particularly if you have a rough or angular aggregate. Then there's also the chemical aspect of that interface to consider. All right, so what is the potential for actual chemical bonding between the cement hydration products and your aggregate? Okay, so that interface can be weak. It depends on if there is chemical bonding. It depends on the texture of aggregate for mechanical. So there can be a few reasons there. So what we set out to determine here was basically evaluate these three key points in the ITZ for concrete with RAP. And I will primarily only be discussing points 1 and 3. We did do some study on 2, but I wouldn't necessarily say that we made much conclusion based on that. Certainly, you'll see that our strongest results, our strongest conclusions, will be from results 1 and 3. So how do we characterize this ITZ? All right. So the best way to do this is using backscattered electron imaging. So this is using an electron microscope, and specifically you need an electron microscope with a backscatter electron detector. Okay, so in order to do this, you need to take your concrete, take a section. So cut a section. You need to backfill the pores with epoxy to stabilize the microstructure, and then you polish it essentially down to a mirror finish. So the final polishing step, at least in this study, was down to a 1/4 micron diamond paste. So in an electron microscope, when electrons are incident onto the sample, there are a number of scattering events. There are a number of different electron energies that will be detected, one of which is something known as backscattered electrons. Those are the electrons that have essentially been generated from interactions with the electrons that penetrate the surface of the material, and then they exit again. So the energy of the backscatter electron is going to be a function of the atomic number of the element that it was interacting with. Okay, and why this is relevant is we can go to the next image to see. So here we're looking at the ITZ of virgin aggregate concrete. So this was a dolomite. Okay, so we do see our aggregate here along the left-hand side. Because of the high iron content in clinker, we find that the unhydrated cement is white. This has been established in a number of studies. So everything white in this image is unhydrated cement. Everything that's a sort of light gray is calcium hydroxide. We abbreviate that CH. I should also note that unhydrated cement, we abbreviate UH. Everything black is epoxy, so those are pores, because again, we have to backfill the pores in the microstructure to stabilize it, so that it doesn't break down upon polishing. So everything black because the epoxy is carbon-based, low atomic number. Those are all pores that appear black. And then everything with an in-between grayscale is hydration products. So CSH, AFT, AFM, it's not really viable to try and distinguish those. So this is now what we can identify. And what we're going to do is use image analysis to assess the ITZ. right? Because since we now have, we know where our aggregate is, right? We're going to have some zone over here that will be the ITZ, right? And then the next zone over here is going to be what we'll call the bulk microstructure. Now, if we look at RAP, so here is a one-day-old. Well, these were essentially mortars because it was just smaller RAP aggregates. There were 3/8 inch aggregates in a cement paste. So here we can see an asphalt mastic, right? So you will see. So I'll basically try and draw where this interface is. So we kind of have this whole interface here. That's all of our asphalt mastic. And so what we see there is quite a number of fine particles, so sand particles and things, embedded in an asphalt matrix. Right? So we call that mastic. Other times we do see an asphalt film with the coarse aggregates, right? In this image, for example, we saw the mastic. So again, same thing here. Everything white is unhydrated cement. This was a one-day-old paste. So there was significantly greater amounts of unhydrated cement. Everything black is still porosity. Everything light gray is still calcium hydroxide. And what I like about this image is you can almost already clearly see quite a bit of high porosity near the interface, right? That appears to be greater porosity in these regions as opposed to out here in the bulk microstructure, right? And this is something that we're going to see in a few minutes with the actual image analysis. And just to show you, right, how smooth these surfaces do become. The right-hand image there is also a backscattered electron image, basically showing surface roughness, right? And so this is the sort of level of fineness that you need to polish the surface to be able to do these types of images. So once we have this compositional backscatter image, there's a number of techniques in the literature that you can use to threshold the different products based on their grayscale value. So in this case, we used the method by Wong, Head, and Bunfeld to basically segment out the porosity. And again, there are other methods to do this. When we look at the grayscale histogram, right, we do see specific segments. So we tend to see a peak here for unhydrated cement. We tend to see a peak for calcium hydroxide and a peak for our hydration products. It's the one that's difficult to determine is this transition from porosity. So once we have basically our grayscale histogram, we can go through and threshold out what each of these materials are, right? So what's unhydrated cement, what's calcium hydroxide, and what's porosity. And just to show you what that looks like, so the method that I had developed was we first need to remove the aggregate. So we just did that with a Photoshop program. So here you have this first image at the top, number 1, we have 2, and we have 3, right? The first image is just the base image we have from our SEM with the aggregate removed. In 2, we have then done that grayscale thresholding. And then 3, we then did some morphological filtering to clean up the image. All right, and again, all of these methods are established in the literature. So once we have that, we need to now establish the ITZ. Okay, and what you should notice is without that aggregate there, right? So without the aggregate shown, we can notice that interface is not uniform, is not smooth, right? That there is a two-dimensional tortuosity to it. So the method that I used based on the literature was to do a 2D Euclidean distance map. And so what that does is essentially finds your nearest neighbor to that interface, right? So it's not a direct one-dimensional offset to generate the ITZ. We're actually considering through this method basically the two-dimensional tortuosity of that interface. Okay, so once we do this process, now we actually can generate our porosity profile in this case, right? So this middle image here is just a binary image where everything white in that middle binary image is essentially everything that was black in this image. It's only the porosity. So based on the grayscale now, you can pull out these different features. Then we do that processing. So in the end, we eventually come to these types of data. So what I'm presenting here is the ITZ characteristics using the procedure that I just had present in the previous few slides. We are comparing our virgin aggregate, which is a dolomite, compared to 3 different RAP sources we looked at, just to compare to see what the differences would be in the ITZ for different RAP sources. Okay, so these had different asphalt contents. These were different asphalt grades, and they had different different virgin aggregates in those RAP. So this is now the average data over anywhere from 50 to 60 images. Right, so this is now collected over many locations in your sample. And the first thing we want to note, so what we're looking at here is either porosity, unhydrated cement, or calcium hydroxide as a function of distance from the aggregate interface, right? So 0.0, right, is immediately at that aggregate interface. So the first thing we notice is the porosity. We can clearly see that there is significantly greater porosity in the ITZ with RAP. Right, and we almost could even visually see that in the image I showed a few slides ago for that one-day paste, right? So we definitely see significantly greater porosity. Unhydrated cement, you know, at least near the ITZ, does not appear to be very different between the dolomite and the RAP, so we didn't really investigate that any further. But the other thing to clearly note is there's a difference in calcium hydroxide at that interface, right? So as we near the area interface, we see there is significantly greater calcium hydroxide for the dolomite, and potentially less calcium hydroxide for the RAP, at least relative to the bulk microstructure. All right, and so this is some of the data that you know, we're still going to be discussing in the coming slides. The calcium hydroxide, we won't really discuss much any further. We will continue to discuss the porosity. One of the most common methods to improve the properties of the ITZ in concrete with virgin aggregates is the addition of silica fume. Okay, and that has been established in many studies. But when we look at the literature with RAP, we find that silica fume does not appear to have as much of a beneficial impact as it does in concrete with virgin aggregates. Okay, and so what we're looking at here is the same RAP source, but now we looked at a mortar with silica fume compared to without silica fume. And what we can find is that it still did not appear to dramatically improve the performance, okay, especially when we compare it to the dolomite. Okay, and so what you can see here, so I'd like to highlight it, right? You will definitely see the addition of the silica fume, yes, did reduce the porosity slightly in the mortar with RAP, but not sufficiently to approach that of the dolomite. So in other words, silica fume just did not appear to be sufficiently beneficial. And indeed, when we do look at the literature, so here's one study from other authors from 2006, you can see that the addition of even up to 20% silica fume did not really affect the compressive strength of concrete. Right, so given the cost of silica fume, it is simply not economical. Right, we don't see sufficient benefit of adding silica fume. So we did investigate this further, and we'll be coming to that in the coming slides with some additional data. So regardless, what we can conclude at this point is that if we look at the ITZ, we definitely know that the presence of the RAP is increasing the size, and I didn't present the data on the size of the ITZ, but we did calculate it based on the porosity. It is a larger ITZ. And it's also more porous, right, relative to concrete with virgin aggregates. So therefore, since you now have a larger volume fraction of a more porous phase in your total composite, we would naturally find a lower modulus, right? So that is one way that we can conclude that yes, we do see a lower modulus in concrete with RAP. This could be one reason why. Is this also the reason for the lower strength? That's hard to say, right? We don't know for certain if that's where our cracks are, if in the ITZ is where our cracks are initiating. It's likely where they may be propagating. We'll see with some coming data that there's more to the story than just the ITZ. So at this point in our research, after doing the ITZ study, we had considered, is it possible to therefore change the chemical affinity between the RAP and the cement to improve any of our properties? All right, and that's what we looked at next. So we wanted to see if we can do some sort of chemical treatment to our RAP to chemically alter the chemistry of the surface of the asphalt to change the chemical bond, and then to see if that would change the properties of the ITZ. So just as a short review on the chemistry of asphalt, so it's primarily a hydrocarbon. It does have heteroatoms of various other elements, so primarily sulfur, nitrogen, and oxygen. Some nickel, some vanadium, some iron, some other minor amounts, but primarily your asphalt is composed of carbon, hydrogen, and sulfur, right? Those are your bulk majority, right? Now, oxidation of the asphalt will increase the number of carbonyls, so carbon-oxygen double bonds, and sulfoxide, sulfur-oxygen double bonds. It'll increase the number of those groups. Now, why are we interested in that? So if we look at the literature, okay, we know that it will be these types of groups that will be likely to bond or complex with calcium inorganic compounds, right? So the idea here was that if we can oxidize this RAP further, we should be able to improve the chemical affinity between our calcium-bearing compounds that are produced from cement hydration with the surface of the asphalt on our RAP particles. All right. So indeed, looking at the literature, we determined a number of different treatments that would likely oxidize the asphalt on the RAP. So we went through a number of different treatments. We'll show some of this data. We also then did compare, just to kind of additionally look at, the effects of silica fume and some other additives, because those are known to improve chemical bonding or the ITZ properties in concrete with virgin aggregates. But here we did not find much improvement with RAP. So I will not really be discussing those concrete additives at the bottom. Instead, I will be focusing here on these oxidizing treatments. So when we do those treatments to our RAP, and then we made various mortars and then measured the dynamic modulus of those mortars, we indeed did find that relative to our control, and our control in this case was normal RAP, untreated RAP. We did not do a control of a virgin aggregate because it would just be very much off the scale. So what we see here is that by oxidizing the asphalt, we do indeed see some improvement, at least to the modulus. But is this sufficient to really give us greater mechanical properties? Probably not sufficiently, right? But at least here we're able to prove that there is some change in our mechanical properties if you oxidize the asphalt. So why is that? Okay, so the next thing we did is looked at the functional groups that were formed upon oxidation. So using these different treatments. All right, so in particular, we used Fourier transform infrared spectroscopy, FTIR, to basically assess what organic functional groups were present. All right, and then basically taking the ratios of the different peak areas, we could then sort of establish, at least relative to these different samples, we could relatively say whether or not one treatment increased the level of oxidation relative to another treatment. And so it's a way you do that. That this is an example of my data. And that this method was basically established in the literature. You can see the citation below, but you basically measure these peak areas and then take the ratio of these peak areas. In particular, the only ones that we're interested here are the carbonyl and the sulfoxide groups, right? Because those are the ones that, according to the literature, should show a stronger chemical affinity with calcium-bearing compounds. Okay, so indeed, when we go through this, when we process the data, we did find that a lot of these treatments, not all of them, but a lot of them did in fact increase the relative amounts of carbonyl and sulfoxide groups, at least relative to the virgin asphalt, right, relative to the control. So now we've established that these different treatment options do indeed oxidize the asphalt. And we've now also established that there may be some evidence of improving the mechanical properties. But what about the actual chemical bond, right? What about the actual chemical affinity to bond? So that's where we quantified bonding using the Cecil drop method. Okay, so in this method, you basically drop a liquid of known properties onto the surface of your material, and you measure the contact angle. Okay, so that contact angle, and you can see examples from high wettability to low wettability. You'll be changing that contact angle, right? So low wettability materials would mean that, for instance, water would bead up. All right, so if you've ever seen water on for example, a Teflon surface, for instance, right, it beads up because it has very, very low wettability. All right, so what we need to do now in this method is to characterize the energy of adhesion. So the way we'll do that is by measuring this contact angle theta, and we'll show how that is in a moment. We're trying to figure out the surface energy properties, right? So surface energy is gamma. We're going to use liquids of known properties. So we know what gamma L is for different liquids. And the way we did this, so we have these two classical equations. So we can combine those two. So now that we now know that basically the energy of the liquid solid interface, so the energy of bonding between the liquid and the solid is just a function of the surface free energy of that liquid and that contact angle. All right. We further used something known as VOCG theory. That's the Van Oss-Chowdhury-Good theory. There are a number of different theories that can be used here and are fairly established. But this theory basically breaks down your surface energy into different components. Okay, so in the end, what we end up with is an equation of three unknowns, and we basically, so our unknowns are all of these properties of the solid. Okay, we use liquids of known properties, so we know the properties of these three for the liquid. Then we measure theta. We also know gamma L. So we essentially need to do three different liquids to get essentially data for three equations to evaluate our three unknowns. All right. And so that's how we do this. And then you can look in the publication to see the actual liquids we used. Here's the example of using ethylene glycol. Here we use just a contact angle measurement device. So you basically, we produce a very flat, smooth surface of asphalt. We do those same oxidizing treatments to it. All right, we have a high resolution camera, an illumination source, and we drop a very small amount of liquid onto the surface. And then the camera is able to measure that contact angle, right? We can see over here. All right, so here is our syringe. You can see the droplet, and then you can clearly see the surface of the asphalt film. So the camera is able to do all of that calculation. So once we have those three equations, we solve for our three unknowns, and then we can go through and calculate some additional properties here. So just a number of different equations. So based on knowing the properties of the two solids, right? So in this case, solids are 1 and 2. So in this case, asphalt, and then we measure this as well for hydrated cement, we can now calculate what the theoretical energy of interaction would be between those two solids. All right, so this would be a theoretical work of adhesion, how much energy it exists at that interface. All right, then you could similarly calculate cohesion, right? So the energy in the material itself. So when we go through and do this, okay, we will immediately notice that, and I didn't show the equation for interfacial energy, but you can look it up in the publication. The interfacial energy is calculated also similarly from these different surface energy values. When we calculate that energy, we find that yes, indeed, as we oxidize the asphalt, we do actually increase that work of adhesion, right? So what would essentially be the chemical bond at that interface, right? So this indeed does prove that these different oxidizing treatments would actually enhance the chemical bond between the asphalt on the RAP and your hydrated cement. Okay, so what this tells us is that this energy of adhesion can increase by up to 11%. Okay, so in other words, the cement has a greater chemical affinity for the oxidized asphalt. Okay, so that is a significant increase. I'm sorry, the interactive energy increased by 11%. The interfacial energy increased by as much as 210%, right? So again, this does suggest very strong energy. However, here is the interesting point. If we calculate the work of adhesion between the cement and the asphalt, we get a value of 65 millijoules per meter squared. If we calculate the work of cohesion of just the asphalt, it's a lower value. So unfortunately, all of this data that we just showed that demonstrates that we can increase the adhesion potential between asphalt and cement is irrelevant, because the energy of cohesion of the asphalt is still lower. So in other words, even though we improved the adhesion energy between cement and asphalt, it still takes less energy to split the asphalt apart. In other words, your cracks are always going to propagate through the asphalt film and not through your ITZ or your cement. right? And indeed, this would be exactly why silica fume has no effect, right? Because yes, silica fume is increasing the properties of the ITZ. It is reducing calcium hydroxide. It's slightly reducing the porosity, but there's no effect on strength. That's again, because even though we improve the ITZ, the cracks still propagate through the asphalt. So there's no benefit of the ITZ. And indeed, looking at quite a number of samples. So here what we did is create a 3-point bend setup where we took a mortar beam, cut it in half, cast an asphalt film at the interface, and then cast new cement mortar on the other half. And when we ran this 3-point bend test, and we also added a notch, so we would attempt to force the crack to propagate through the interface. All of our tests only failed in asphalt cohesion. We could not get an asphalt adhesion failure. Okay, and again, that completely supports the previous finding from the surface energy characteristics calculations. So in the end, this is the primary two conclusions that we've been able to draw from this work. So we do know that RAP in concretes will reduce the mechanical properties, so the strength and modulus. So number one, that is going to be due to the larger, more porous ITZ, right? So again, because of that, we have a larger volume fraction of our concrete is a more porous phase, which of course would have reduced our modulus. Could also affect strength, assuming that it would allow for easier crack initiation, possibly propagation as well. The other reason for our reductions in properties are because of the cohesive failure of the asphalt, right? So again, even though we can improve the properties of the ITZ, right? So the silica fume can improve it slightly, maybe changing the water cement ratio. Doesn't matter even if we dramatically improve the ITZ, it would still indicate that our material will always fail through cohesive failure of the asphalt, right? And that's probably one of our primary effects of why we see these differences in mechanical properties. So everything I've shown so far is data that we've already published. I do have some new data that I'd like to share. We will have a forthcoming publication. Hopefully we plan to submit it early 2022. So now that we know all of this, right? We know that silica fume does not appear to improve anything. The question is why? Why is this, right? Why is RAP causing this increase in porosity in the ITZ, right? Again, once we can solve that question, we might actually, be able to start to fix the ITZ, and then we can also start to look at fixing the cohesive failure as well. So in understanding why this is, why doesn't silica fume do anything? Well, our primary hypothesis has to deal with that we suspected and then proved that the high pH pore solution of the concrete is actually leaching organic compounds from the asphalt. Okay, and so what we did, so here's some of the data from a forthcoming study that we'll be publishing. We found that if we soak RAP in a high pH solution, so something similar to a concrete pore solution, then we also did compare it to plain deionized water. We did find that in a high pH solution, we do generate a high total organic carbon content in the solution. Now some of the data that we're working on right now is figuring out what those compounds are, right? Because we do know from the literature from a number of studies that certain organic compounds will detrimentally affect cement hydration. And that could be what's happening here. All right, so in the immediate environment around the ITZ, if we're getting a leaching of some organic compounds from the RAP, that may only just stay in the region of the ITZ and affect the cement hydration in that localized region, right? And if it is indeed delaying or retarding cement hydration, that might be why we're seeing such a high porosity. But again, we have more data that we'll be publishing on this in the coming months. So a few things we'd still like to figure out that we hope to keep working on, right? Is as I showed on the previous slide, is figuring out why do we see this larger, more porous ITZ. Once we know that, can we figure out a treatment option so that we don't get a larger, more porous ITZ, right? And then we also have to somehow fix this cohesive failure, right? And that may be the more challenging one, right? Because we do know that we have the ITZ issue, and then we have the cohesive failure issue, both of which are what's affecting the mechanical properties of RAP and concrete. So we really need to look at both of those issues before we can hope to improve the properties of our concrete. So with that, I'd like to thank you for your attention. Below is my contact information. If you're interested to know more about this research, if you're interested in opportunities for collaboration, I'd be more than happy to talk with you. So thank you for your attention.